In this video, we're going to prove that this ring, z adjoin 1 plus root negative 19 over 2, is not a Euclidean domain. So this is a tricky proof. We're going to use the following three facts. So first, the only units of this ring are plus and minus 1. Second, the ideals generated by 2 and 3 are maximal in this ring. And then the third fact is a more general fact about Euclidean domains that contain non-zero non-units. And that's that, in any such Euclidean domain, there's at least one element such that the following are true. So this element m is not 0 and is not a unit. If I choose any non-zero non-unit x, the image of x under the Euclidean function is at least as big as m. So this is kind of like the minimal image under the Euclidean function that you can get. And then the third property is that R over the ideal generated by m, the cosets all have representatives that are units of R or 0. Okay, so this is true for any Euclidean domain that has non-zero non-units, which you can prove. Great. So we're going to use these three facts. And we're going to start. I'm going to assume for contradiction that this given ring, so z 1 plus root negative 19 over 2, is Euclidean. With Euclidean function f. Okay, and we showed, or we're using the fact, that there's only two units in this ring, which is plus and minus 1. And so there's definitely non-zero non-units in this ring because it's infinitely large. So therefore, we know there exists, by our fact 3, m and r, such that all the things we said, so m is not 0, m is not a unit, f of m is minimal among non-zero non-units. And then there's the other thing about the quotient being represented by only units of r and 0, but we're not going to use that yet. That's going to come later. Great. So it's not totally obvious why this is useful, but it turns out that the trick is to divide 2 by m. So 2, which is in this ring R, is equal to the following. And here we're using our assumption that it's a Euclidean domain, right? So we know that there's a Euclidean algorithm, and so we know that 2 is equal to mq plus r, where q and r are elements of the ring R, and either f of r is strictly less than f of m or r is 0. Okay, but by our fact, we know that f of m is minimal among non-zero non-units, right? And so if f of r is less than f of m, that forces r to be a unit. And so there's actually three cases for r then. One case is that r is -1. Actually, let's say one case is that r is plus 1. One case is that r is -1. And then the last case is that r is 0. Right, and here we're using, again, that the only units in the ring are positive and -1. Great. So we're going to look at each of these cases and we'll show that each one gives a contradiction. So the first case is that r is 1. This is actually easy to see why this gives us a contradiction, because then 2 is equal to mq plus 1. And what that means is that 1 is equal to mq, and so m is a unit, right? Because you can multiply m by something in the ring and get 1. And we know that this can't happen because we assumed that m is a non-zero, non-unit. So we know that this can't happen. Great, so the other two cases are a little bit more complicated. So if r is negative 1, in this case we get that 2 is equal to mq minus 1, and so we get that 3 is equal to mq. Right, and so now what we want to do is we want to use another one of our facts, right? Remember that the ideal generated by 3 is maximal. All right, this is the second fact that we had. And this fact that 3 is equal to mq tells us that the ideal generated by 3 is contained in the ideal generated by m, right? Because 3 is a multiple of m. But the only way that this can happen, because 3 is maximal, is if the ideal generated by 3 is equal to the ideal generated by m. And we know that r over m, which this equals r over 3, is represented by units of r and 0. And there's only 3 elements in that list. It's just negative 1, 1, and 0. Great. And so in particular, these are all integers. And so we'll use that to get a contradiction. So now consider this number, 1 plus root negative 19. So this is an element of the ring, certainly. And we know that its coset in this quotient is represented by one of these numbers. So basically what that tells us is that 1 plus root negative 19 is actually congruent modulo the ideal generated by m to one of these numbers. So in other words, we know that, the ideal generated by 3, sorry, because it's r over the ideal generated by 3. So we know that there exist x and y such that this is true, right? Because this is an element of the ideal generated by 3. And so we know that this sum is equal to some k, where k is one of the numbers that we said, right? So k is plus or minus 1 or 0. And so I claim that this can't happen because if you distribute everything out here and then you compare coefficients, you get the following. You get 1 plus 3y over 2 is equal to k. Or sorry, that 1 plus 3y over 2 is equal to 0, right? And you get that by just distributing everything out. You have root negative 19, you have 3 times y over 2, and that's equal to the coefficient of root negative 19 over here, which is 0, right? But I'm going to claim that this can't happen, so this is a contradiction, because this tells me that 3y over 2 is equal to negative 1, and then that tells me that y is negative 2/3. And this is impossible because these numbers x and y are integer coefficients, because this is how the ring z1 plus root negative 19 over 2 works. It's just integer linear combinations of these numbers. And so this is impossible. And so that takes care of the first two cases. If you remember, the three cases for R was that R is 1, -1, or 0. So the final case would be if R is equal to 0. And that gives us that 2 is equal to MQ. So there's a similar argument here. This tells you that the ideal generated by 2 is contained in ideal generated by M. And we know, again, from our fact that the ideal generated by 2 is maximal. So then, similar argument to the previous case, that the ideal generated by 2 has to equal the ideal generated by M, because ideal generated by 2 is maximal. So this tells us that these two quotients are equal. Right, and so we can make a similar argument as before, that now the cosets of this quotient are represented by plus and minus 1 and 0. So now we want to do a similar trick. Remember, before we took 1 plus root negative 19, and we argued that that was congruent modulo the ideal generated by 3 to something. And now we want to do a similar thing, but we want to do it with 1 plus root negative 19 over 2, okay, which is also in R. And so we know that, this plus some multiple of 2, so this is going to be 2x plus y, 1 plus root negative 19 over 2, like this. X and y are both integers. And we know that, again, this is equal to k, where k is in the set 0 plus or minus 1. Okay, and so this is going to be a contradiction by kind of a similar approach to before, that now if you distribute and compare coefficients, right, here I have root negative 19 over 2, and then here I have 2 times y times root negative 19 over 2. So my coefficient over here is just 1/2 plus y. So I have 1/2 plus y root negative 19. And then I guess I have 1/2 plus 2x as well. And then over here, I have that this is equal to k, and then basically plus 0 times root negative 19, because k is an integer. Right, and so what this tells me, compare coefficients again, is that 1/2 plus y is 0. And then this tells me that y is negative 1/2, which again is a contradiction because y was assumed to be an integer. Okay, so that actually completes the proof. There were 3 cases. We basically took a non-zero non-unit that had a minimal Euclidean norm, and we showed that it can't be a divisor of 2. And so that's the end of the proof. Thank you for watching.